Hi, and welcome to this tutorial of modeling a thick beam as a 2D shell in PATRAN. We can use, for the new model preferences, we can use tolerances based on model. The approximate model dimension is 1000, corresponding to the length of the beam, which is 1000 millimeters. Analysis code Nastran, and it's a structural analysis. So let us start by defining the geometry. The geometry, we can define it as a surface. For the method I use XYZ, which is in my opinion the easiest method for defining a rectangular surface. So I would like to have the middle of the beam, the middle of the left edge at 0, 0, 0. So when I define the lower left corner, I say minus 40, and I use a vector of 1000 in x direction and 80, which is the height of the beam, in y direction, and then I hit apply. You see here a surface is created. This is all we need to do for the geometry. So we can go on to properties and define the material. We pick an isotropic material with manual input. Let's call this material mod1. The input properties, the elastic modulus was given as 13,500 MPa or Newton per square millimeter. The Poisson's ratio can be derived to be 0.35, corresponding to the given shear modulus. And this is all we need to define. So I can click OK and then hit apply. And we can see now that material 1 has been created. So now let's go on to define the property. We want to create a 2D shell. The thickness is the B dimension of the beam, which is 40. So 40. Material property, we define the material here. You can use mod1. We don't need to define an orientation. That's for mostly when you use orthotropic properties. So we're actually done here now. So I hit OK. You can select an application region, a geometry. So we pick surface 1, we add it, and we hit OK. And we call this guy prop 1 and hit apply. So now when I hit prop 1, I see that this worked and that the application region is surface 1. So now we can go on to loads and boundary conditions. So let's start with defining the clamping at the left edge. So what we want to do is define a displacement. Input data. All translations are 0. And all rotations are 0. So I say OK. I select the application region. What I want is an edge. And I want this edge. So surface 1.1. I say add. I click OK. And I hit apply. Yeah, let's just define this as clamp. And apply again. So now you see 1, 2, 3, 4, 5, 6, all degrees of freedom fixed at this edge. For the load, we want to define a shear load at the right edge of the beam. Now when you look at the derivation given in the reference video of the problem description, when you define a Timoshenko beam, you define the shear as a shear load applied to the surface of the tip of the beam. So we don't want to use a force, which is a nodal force, because that's a point load. And in reality, it's not really a point load, it's a shear load distributed over the tip of the beam. So what we're going to do is define a CID, distributed load. We can call this load P. We do input data, the surface distributed load, which is 0. We want to apply an edge distributed load to this edge here with in y direction. So the load in y direction is in total 10,000 newtons or 10 kilonewtons, and it's distributed over a height of 80 millimeters. So what we can do is divide 10,000 by 80, which comes out to be 125. So we define this as minus 125, then chord 0, with this, with y direction as defined in chord 0. We can click OK. We can set an application region, select surfaces or edges. We can select this edge, we can add it, OK, and hit apply. And now you see the edge load is being created. So what we want to do now is mesh the part. So we go to the meshing module. We want to start by giving it a mesh seed to arrive at a well-structured mesh. Now one thing to think about is how many elements do I want through the height of the beam, because we expect the stresses to vary through the height of the beam as there are bending stresses. So using just one element would be a mistake, because it doesn't really allow us to see tension or bending very well at the extremes, and it will give us a virtual extra stiffness that's unwanted. So let us start by doing 2 elements. This is not necessarily the best thing to do, and we're gonna look at what happens if we increase the number of elements in a later stage. So for the curves, we pick this curve here and this curve here, and we do apply, and we see the mesh sheet has been created. For the mesh sheet along the length of the beam, we need to consider that the curvature is changing over the length. So where the boundary conditions are applied, these are strong boundary conditions, and they may result in stress concentration factors that were not really physical and also not very interesting to us. And this at this section the beam will stay more or less straight, and it will start to curve more towards the tip, in increasing its radius of curvature. So what we want to do is use more elements here and use less elements here. So we're going to go for a biased mesh. So we pick one-way bias, and we look here at this figure. So it says L1 is defined at the left and L2 is defined at the right, with left and right according to this little arrow that's displayed. So we're going to use a total of 20 elements, and we want to have a ratio of 5, with the smaller elements being here, so we pick 1/5. For the curves we select the top and bottom, and we hit apply. So now we can actually mesh the part. It's a surface, select surface 1. An ISO mesh with quad 4 elements is fine. We don't need to select the property because we already applied the property to the geometry, so we can hit apply. You can see a mesh is created here. And when you look at the aspect ratios of the elements, you see the elements here are almost square, these two, and the aspect ratios here and here are suboptimal, which is not necessarily a good thing, but let's just see what happens if we run the analysis like this. First, I always want to check if the properties have been transferred correctly, so we can do show thickness as a fringe and apply, and you see, yeah, the thickness has been defined as 40, which is correct. So let's clean up this one and go to the analysis module. So we want to run the entire model and a full run. The solution type is a Sol 101, a linear static one. We don't need any subcases, as we just have one load and one boundary condition that's constant. So we can run the model like this. So it's running and it's finished. So now we need to attach the results. So you go to Access Results, attach XDB, select the results file. This always takes a while. Apply. The results have been attached. So when we go to the results module, we want to do a quick plot. Let's plot the von Mises stress and the displacements. And for the fringe attributes, we want to use an element fill because we want to see element stresses. And we hit apply. So what we see here is that the bending stress is not very much visible because we use the von Mises stress, which is always possible and which is always positive. So it might be more interesting is to look at the stresses in x direction. Now we can clearly see that we have tension in the top and compression in the bottom. And as we move towards the tip of the beam, the bending stress is reduced because the moment is reducing. And we have no bending here at the tip, just a pure shear stress. So when we look at the stress distribution like this, we see that there's no there's no way to see a linear distribution through the height of the beam as we expect for the bending stress, because we only use 2 elements. So let's go to a finer mesh and see what happens. And we see the maximum displacement came out to be 144 millimeters, which is here. So let's go back to the meshing module and clean up the figure. First I want to delete the existing mesh. Create a new mesh sheet. So let's increase this to 40. We can leave this the same, the ratio too. And through the height of the beam, we still want to use the uniform mesh sheet, but instead of 2 we want to use 10 now. Apply. And when we create a mesh, we see that we have much better aspect ratios at the tip of the beam, where it's almost square, and more elongated elements as we go back. So this is actually a nice result. So let's run the analysis again. We want to overwrite, and we allow the delete the files. Access the results. Attach XDB, select results file. When we go back to the stress tensor, hit apply. Now we can very clearly see how the stresses vary through the thickness, so a much nicer representation of the bending stress. Still we can see that as we go to the tip of the beam, that the bending stresses are less dominant and are completely gone at the tip of the beam, and the maximum displacement came out to be minus 145 millimeters. So let's see what the exact displacement is at the last node. In Y direction. Minus 144.58. When you look at the solution from Amicus, it came out to be minus 144.7, so that's almost the same. Well, thank you for watching. I hope you learned something, and I hope you're able to reproduce these results for yourself.